Yes, good morning, everyone, and welcome to the online education for the English medium organized by the Municipal Corporation of Greater Mumbai. So today we are going to study the subject science for class 9, and the topic is study of sound. Now this is the fourth session in the series. So in the previous three sessions we have completed the chapter. In today's sessions we are going to revise the chapter again in detail, and we are going to solve numericals relating to all the topics, right? So my name is Vishal Sudhir Chaudhary, and I am from the Kurar Village MPS English Secondary School. Now, so the topics that we have covered in this chapter are relating to sound waves, velocity of sound, reflection of sound, the human ear, audible sound, infrasonic sound, and ultrasound, right? So within these topics, the subtopics that we have covered is relating to what? The definition of sound. Then we have seen the properties of sound waves. Then we have seen the types of waves, that is longitudinal waves and transverse waves. Then we have seen the different characteristics of sound waves. Then we have studied the concepts relating to velocity of sound and the variation in velocity of sound. After that, we studied in detail about the types of sound, that is audible sound, infrasound, and ultrasound. Then we moved on to the concept of reflection of sound. So in the concept of reflection of sound, we studied the phenomena of echo and reverberation, right? And also concepts relating to sonar and sonography. In the last part of the chapter, we studied the human ear, right? So let us begin in detail about the revision of the chapter. So first we saw this definition of sound. So sound is a form of energy which creates a sensation of hearing in our ears, and sound energy travels in the form of waves. We know that a medium is necessary for the propagation of the sound waves. So as you can see in this diagram, the speaker, which is the source of the sound, it vibrates and it generates those sound waves, right, which travel away from the speaker in all directions. Next, sound waves gives rise to a chain of compressions and rarefactions of the medium, right? So compressions are regions of high pressure and rarefactions are regions of low pressure, right? So as you can see, when a particle vibrates, what happens is these waves move away from the source of the sound in the form of alternate bands of compressions and rarefactions. Okay, then the longitudinal waves. So in a longitudinal wave, the particles of the medium oscillate about their mean positions in a direction parallel to the propagation of the wave. So in this case, you can see the particle happens to oscillate from left to right, whereas the wave also travels on the screen from left hand side to the right hand side. So the direction of vibration of the particle and the direction of the wave, they both are parallel to each other, which is the case in longitudinal waves, right? So a sound wave can be shown in the form of a graph. At any moment during the propagation of a sound wave, we can find alternate bands of compressions and rarefactions of the medium, that is the bands of high and low density, as we have seen previously in this diagram, right? So compressions are shown with bands of dark color, whereas rarefactions are shown with bands of faint color, which are spaced far apart. Okay, then velocity of sound. The distance covered by a point on the wave in unit time is the velocity of the sound wave. We know velocity equals to distance upon time. Any point on the sound wave covers a distance equal to lambda, which is wavelength, in time t, which is the time period. Thus, the velocity is given by v equals to nu into lambda, where nu is the frequency and lambda is the wavelength of the sound wave. So we know as 1 upon t is nu, we can write velocity equals to wavelength upon time period, that is v equals to lambda upon t, right? So velocity of sound equals to wavelength into frequency. So in any medium at fixed physical conditions, the velocity of sound of different frequencies is very nearly the same. The velocity of sound is highest in solids and least in the gases. It increases with an increase in temperature of the medium, right? So we also saw the variation in velocity of sound means for a given medium, how does the velocity of sound change with changes in different conditions. So the first one is what? Variation with temperature. So velocity of sound is directly proportional to the square root of temperature. Then variation with density. Velocity of sound is inversely proportional to square root of density. And variation with molecular weight. Velocity of sound is inversely proportional to square root of the molecular weight. Then we saw the different types of sound. So the different types of sounds are based on the frequencies of the sound and the ability of us humans to listen to those sounds or not. So the first type of sound is called the audible sound, which us humans can hear. So audible sounds have a frequency of 20 hertz to 20,000 hertz. The next one is what your infrasound. So infrasound has a frequency that is lower than 20 hertz, and ultrasound has a frequency higher than 20,000 hertz. Right? The next is, let us see in detail about these three types of sounds. So audible sound, the limit of the human ear are, the limits of hearing of the human ear are 20 hertz to 20,000 hertz. The human ear can hear sound frequencies in this range. These sounds are called as audible sounds. Human ears cannot hear frequencies lower than 20 hertz and higher than 20,000 hertz. Next is infrasound. Sound waves with frequency smaller than 20 hertz are called infrasound. The sound produced by a pendulum and the sounds generated by the vibration of the Earth's crust just before an earthquake are the examples of infrasound. Next is ultrasound. Sound waves with frequency greater than 20,000 hertz or 20 kilohertz are called ultrasound. Dogs, mouse, bats, dolphins, etc. have the special ability to hear ultrasonic sounds. They can sense some noise which are inaudible to us humans. Children under 5 years of age and some creatures and insects can hear frequencies up to 25,000 hertz, that is 25 kilohertz. Next, bats, mice, dolphins, etc. can also produce ultrasound. Ultrasound is also used for communication between ships at sea, where you do not have any cellular services or you do not have any internet facilities, right? Then it is used to obtain images of internal organs in a human body, right, which we have studied in the concept of sonography. Then ultrasound is also used to locate cracks and faults in the metal blocks. As you can see in the diagram here, the bats make use of ultrasound to find and detect the location of the prey, and that is to find the food. Okay. The next is what the concept of reflection of sound. So we know that the sound waves also obey all the laws of reflection, just like light waves. Okay. So in this case, you can see there is a hard plywood surface which is kept there for reflection of the sound, and there is a partition made up of soft wood. On one side of the partition, we have placed a stopwatch, and we are trying to listen to the sound of the stopwatch from the other side of the soft wood partition. Then we have just placed the cardboard tube so that the sound waves can travel through these tubes. Okay, so on observation is found that the angle of incidence made by the sound waves is equal to the angle of reflected sound waves. This proves that angle of incidence equals to angle of reflection, right? Then next we saw about the types of reflectors, right? The reflectors of sound are of two types, that is good and bad reflectors of sound. How much of the incident sound gets reflected decides whether a reflector is a good or a bad reflector. A hard and a flat surface is a good reflector, while clothes, paper, curtains, carpet, furniture, etc. absorb sound instead of reflecting it. Hence, they are bad reflectors. So, if you can see in the diagram here, the incident sound waves are shown in the red color, right? Some of the sound waves they get reflected, which are shown in the blue color, right? Out of the incident sound, some of it gets absorbed into the reflecting surface, and some of it is transmitted, means it goes onto the other side of the wall, right? So that means some of the sound is absorbed and transmitted, right? This decreases the amount of reflected sound, right? Next, one of the important phenomena that we have studied relating to reflection of sound is called as an echo. So an echo is a repetition of the original sound because of reflection from some surface. At 22 degrees Celsius, the velocity of sound in air is 344 meters per second. Our brain retains this sound for a time interval of 0.1 seconds. That means whenever any sound enters into our ears, it is registered in our brain as sound, and we perceive it as a sensation of hearing. So whenever a given frequency enters into our brain loses the ability to listen to that same frequency for a time interval of 0.1 seconds. Thus, For us to be able to hear a distinct echo, the sound should take more than 0.1 seconds after starting from the source to get reflected and come back to us. Okay, so we can determine the minimum distance between the source and the reflecting surface as follows. So we know speed equals to distance upon time. So we can write distance equal to speed multiplied by time, which is 344 meters per second multiplied by 0.1 seconds. So we get 34.4 meters. Now remember, the 34.4 meters is a total distance. That means from the source to the reflecting surface and then back again to the source, right? Thus, to be able to hear a distinct echo, the reflecting surface should be at a minimum distance of half of the above, that is half of 34.4, which is 17.2 meters, right? The next concept we studied was about reverberation. So reverberation is an undesirable property relating to reflection of sound. So sound waves get reflected from the walls and roof of a room multiple times. Repeated reflections of sound waves from the walls combine to build up what seems like a continuous sound. Okay, this causes a single sound to be heard not once but continuously, and this is called as reverberation. Okay, then some auditoriums, public halls, or buildings are considered acoustically poor because of reverberation. To reduce reverberation, the roof and walls of auditoriums are generally covered with sound absorbing materials such as compressed fiber boards, rough plaster, or curtains. Even the materials of the seats is chosen such that it absorbs the sound waves to the desired extent. Right? Next, we study the concept of sonar. Sonar is a short form for sound navigation and ranging. It is used to determine the direction, distance, and speed of an underwater object with the help of ultrasonic sound waves. And sonar has a transmitter and a receiver which are fitted on ships or boats. Okay, the transmitter produces and transmits ultrasonic sound waves. These waves travel through the water, strike underwater objects, and get reflected by them. The reflected waves are then received by the receiver on the ship, and a computer is used to analyze and create a image on the computer screen. So the receiver converts the ultrasonic sound into electrical signals, and these signals are properly interpreted. The time difference between transmission and reception is noted, and this time and velocity of sound water give the distance from the ship of the object which reflects the sound waves. Sonar is used to determine the depth of the sea and to search for underwater hills, valleys, then submarines, icebergs, or any sunken ships. Right? Then the next concept we studied was sonography. A sonography technology uses ultrasonic sound waves to generate images of internal organs of the human body. This is useful in finding out the cause of swelling, infection, or pain. Okay, the condition of the heart, the state of the heart after a heart attack, as well as the growth of the fetus inside the womb of a pregnant woman are studied using sonography. Right? Then, the sonography technique makes use of a probe and a gel. As you can see in the diagram in the center, the probe is a handheld device. It is just a device which you can hold in your hands, right? And a gel is applied where you want to observe inside the body. So the gel is used to make proper contact between the skin and the probe so that the full capacity of the ultrasound can be utilized. Means the gel which is applied helps to transfer the ultrasonic sound waves from the probe into the human body. Okay, the gel is applied to the skin outside the internal organ to be studied. High frequency ultrasound is transmitted inside the body with the help of that probe. The sound gets reflected from the internal organs, is again collected by the probe. That means the probe has the transmitter as well as the receiver. So it does both the jobs of transmitting the ultrasonic sound waves into the body and also receiving the reflected ultrasonic sound coming from the body. Okay, so the sound reflected from the internal organ is again collected by the probe and fed to a computer which generates the images of the internal organ. As this method is painless, it is increasingly used in medical practice for correct diagnosis. That means there is no operation required, there is no need for the patient to get admitted, and it is a completely painless procedure, and it can be done within 10 to 15 minutes. Okay, Then the next concept we studied was about the very important organ, one of the important sensory organs, that is your human ear. Now, the ear is an important organ of the human body. We hear sounds because of our ear. When sound waves fall on the eardrum, it vibrates, and these vibrations are converted into electrical signals which travel to the brain through the nerves. Now, let us see the three parts of the human ear. Now, the human ear can be divided into three parts, which is the first one, the outer ear, the part that we can see up from outside. Then the second is the middle ear, and the third is the inner ear. Let us see all these three parts in detail. So the outer ear, also called as the pinna, is the part that we can see from outside. So the outer ear collects the sound waves and passes them through a tube to a cavity in the middle ear. It is a peculiar funnel-like shape which helps to collect and pass sounds into the middle ear. So the only function of the outer ear is to collect the sound waves coming from different directions and concentrate them or pass them into the middle ear, right? Then the second part is the middle ear. There is a thin membrane in the cavity of the middle ear which is called as the eardrum. When a compression in the sound wave reaches the eardrum, the pressure outside it increases and it gets pushed inwards. The opposite happens when a rarefaction reaches there. So the pressure outside decreases and the membrane gets pulled outwards. Thus, sound waves cause vibrations of the membrane. That means when a compression reaches the eardrum, the eardrum is pushed inwards. When a rarefaction reaches the eardrum, it gets pulled outwards. That means the eardrum starts vibrating with the same frequency of the sound wave, right? Then, as you can see in the diagram, you can see the eardrum starts vibrating with the same frequency of the sound wave. These vibrations are transferred onto the middle ear, right? Inside where you have the three bones, and these three bones then transfer these vibrations onto the cochlea, right? Let us study further. Now the inner ear. The auditory nerve connects the inner ear to the brain. The inner ear has a structure resembling the shell of a snail. It is called as a cochlea. Now the function of the cochlea is to receive the vibrations coming from the membrane and convert them into electrical signals which are sent to the brain through the auditory nerve, and the brain then analyzes these signals and we perceive the sensation of hearing, right? So this is the part that we have seen so far, the whole theory of the chapter. Now let us discuss all the numericals that we have for the session. Okay, now let us look at the first numerical example. How long will it take for a sound wave of 25 centimeter wavelength and 1.5 kilohertz frequency to travel a distance of 1.5 kilometers, right? So whenever you have any numerical problem, first of all you need to do is to write down all the given things, right? All the given variables, whatever they are there. So we'll write down given. The first is frequency. The frequency symbol is mu. It is given as 1.5 kilohertz, right? So you all have to convert them into the SI system, means MKS system. So 1.5 kilohertz, so 1 hertz or 1 kilohertz is 1000 hertz. So you can write down 1.5 kilohertz is equal to 1.5 into 10 raised to 3 hertz, means 1 kilohertz is 1000 hertz. That is 10 raised to 3. Okay. Then next is what? Given parameter is wavelength, which is lambda. So you can write lambda is 25 centimeter. Again, we have to convert from centimeter to meter, which is the standard unit, right? So we know 1 meter is 100 centimeters. That means 25 centimeter will be 1 upon 4 meter, that is 0.25 meters. Okay. The next is distance. Distance S is given as 1.5 kilometers. That is equal to 1.5 into 10 raised to 3 meter. Again, we are converting kilometers to meters, and we are aware 1 kilometer is 1000 meters. So the factor is 10 raised to 3. Okay. We need to calculate time. Now let us first of all start with the formula. Now because we have to calculate time, first we need to calculate velocity of the sound. So we know velocity of sound is equal to frequency into wavelength. So V equals to nu into lambda, right? So we have the value of nu as 1.5 into 10 raised to 3, which is the frequency, and we have the wavelength as 0.25 meters. So we multiply them, that is 1.5 into 10 raised to 3 multiplied by 0.25. So we get V, that is velocity of sound, is equal to 0.375 multiplied by 10 raised to 3. That is equal to 375 meters per second, right? Once we get the velocity, we can calculate the time. Let us see. We know velocity equals to distance upon time, right? So we can write time is equal to distance upon velocity. So time t equals to s upon v, right? Now the distance traveled we have taken as 1.5 kilometers, that is 1.5 into 10 raised to 3 meters. So we can substitute it here. So t is equal to s upon v, that is 1.5 to 10 raised to 3 divided by velocity, which we calculated here at the bottom. Can you see 375 meter per second? So we have substituted here. So we get 1.5 to 10 raised to 3 divided by 375, that is equal to 1500 divided by 375. That comes down to 4 seconds, right? So the final answer time required is 4 seconds. Always make a habit of writing the final answer in the form of a statement, right? So you can write thus: the sound wave takes 4 seconds to travel the distance of 1.5 kilometers, right? Which is the question that is being asked. Okay. So let us now move to the next question. Number 2. Ultrasonic waves are transmitted downwards into the sea with the help of a sonar. Okay. So you can see there is a sonar device which transmits sonar waves towards the bottom of the sea. Fine. What they have given. The reflected sound is received after 4 seconds. So once you have sent the waves downwards, it takes some time to get reflected and come back. That time is 4 seconds. Okay. What is the depth of the sea at that place? So we need to calculate the depth of the sea. Okay. One given fact is velocity of sound in sea water is 1550 meters per second. Okay. Now let us see. That given the velocity of sound we have written as 1550 meters per second. Okay. The time required for the echo to be heard is 4 seconds. Then time taken by the sound waves to reach the bottom of the sea is 4 divided by 2, that is 2 seconds. Now how do we get this? Now if you come back to your diagram here, where is it? This one. You can see if you are measuring the depth of the sea, you can see the transmitted pulse first of all travels the distance from the ship to the sea floor, correct? And it will take some time. Then when it comes from the sea floor back to the ship, it will take some time, right? That means it is traveling the same distance twice. Okay. So let us come back to the question. What does it have? There. Okay. So the time taken by the sound waves to reach the bottom of the sea is 4 by 2, that equals to 2 seconds. So you can see velocity of sound is distance upon time, right? So distance is equal to velocity of time velocity of sound multiplied by time. The velocity of sound given is 1550 multiplied by 4 divided by 2, which is the time taken, that is 2 seconds, right? So there is a mistake here. It should be 4 divided by 2, or you can write 2 seconds. That comes down to 3100 meters. So you can say the depth of the sea at the place is 3100 meters, right? That is the second question, right? Next question is what? Let us see. The speed of sound in air at 0 degrees Celsius is 332 meters per second. Okay, that is a given. If it increases at a rate of 0.6 meter per second per degree, what will be the temperature when the velocity has increased to 344 meters per second? So what they have given is, for a given temperature, say x, at that temperature, or at the temperature 0 degrees Celsius, the speed is 332 meters per second. Fine. Now for every 1 degree rise in temperature, see, if it increases at a rate of 0.6 meter per second per degree, that means for every 1 degree rise in temperature, the velocity increases by 0.6. That means if at 0 degrees Celsius, the speed is 332, that means at 1 degree Celsius, it must be 332.6, because it increases by 0.6, right? What they have asked is, what will be the temperature when velocity has increased to 344? That we have to calculate. So let us see what do we do. Let us see the solution. The speed of sound in air at 0 degrees Celsius is 332 meters per second. Fine. If it increases at the rate of 0.6 meter per second per degree, then the speed at x degrees Celsius will be 332 plus 0.6. Okay, that will be 332 plus 0.6 times degree Celsius. Thus, 344 equals to 332 plus 0.6x. So we can calculate this. We can take the numbers on one side. So 344 minus 332 equals to 0.6, and 344 minus 332 is 12. So we can say 12 equal to 0.6x. Therefore, we get x equals to 12 divided by 0.6. That comes down to 20 degrees Celsius, right? So the temperature of the air will be 20 degrees Celsius when the velocity of sound is 344 meter per second, right? Then the next question is what? Let us see. Nita heard the sound of lightning 4 seconds after seeing it. Okay, so Nita is standing somewhere, and there happens to be a lightning strike somewhere. Now remember, whenever there is a thunderstorm, you will always see the lightning first, and then after some time the sound will come to you. That is a thunder. So lightning and thunder. So you see the lightning first, and then you get the thunder, which is the sound. Okay, why is it so? Because light travels at a very high speed, that is 3 into 10 raised to 8, means 3 lakh kilometer per second. Right, is the speed of the light. But sound travels much slower, around 340 meter per second. Right. So whenever you have a source where you have lightning or a light along with a sound, the light will always come first. Okay. So let us see. Nita heard the sound of a lightning 4 seconds after seeing it. What was the distance of the lightning from her, right? From her. So the velocity of sound in air they have given as 340 meters per second. Let us see the solution. Let the distance between Nita and the source of lightning be x. Okay. So speed of sound in air they have given as 340 meters per second. Time taken by the sound to reach Nita is 4 seconds. We know velocity of sound equals to distance upon time. So you can write distance is equal to velocity of sound multiplied by time. Right. So velocity of sound they have given as 340 meters per second. And time required for the sound to travel is 4 seconds. So that equals to 340 multiplied by 4, that equals to 1360 meters. Thus, the distance of lightning from Nita was 1360 meters. Now, you can observe this kind of an example in your day-to-day life. Now, during the monsoon season, we have frequent thunderstorms, right? So, whenever you see a flash of light, right, you can just count in your head amount of seconds. Once you see the flash, you can count 1, 2, or you can count like tick tick 1, tick tick 2, tick tick 3, tick tick 4, and then you get the sound. So you can come to know, okay, it took 4 seconds for the sound to come. And then by using this concept, we can calculate how far the lightning must have struck from your position. Right? This is a simple example. Then let us see the next example. Now, Sunil is standing between two walls. The walls closest to him is at a distance of 360 meters. If he shouts, he hears the first echo after 4 seconds and another after 2 seconds. Right? What have they asked? What is the velocity of sound in air? And second, what is the distance between the two walls? Now here you can imagine that the person Sunil is standing in between, and there is a wall in front of him and a wall behind him. Or you can imagine there is a wall to the left hand side of Sunil and one wall is towards the right hand side. So when he shouts, we know that sound will travel equally in all directions. So the sound will go to one of the wall on the right hand side, and also it will travel towards the wall on his left hand side. Right? Now, what they say that he hears the first echo after 4 seconds and another after further 2 seconds. That means the walls must be quite far away, more than 17.2 meters, just we studied. Let us discuss this. Let us see. Look at the solution. The time to hear the first echo is 4 seconds. Distance traveled by the sound in the 4 seconds is 360 multiplied by 2. Right? Okay. Why have we taken multiplied by 2? Why have we taken distance traveled as twice? Because the sound will travel from Sunil up to the wall, and then again it has to come back, right? So it has traveled double the distance. That is why we have taken the distance traveled as twice the distance. Okay, and the first wall is at a distance of 360 meters. So we can see speed of sound is equal to distance upon time. So distance is equal to 360 multiplied by 2 divided by 4. Right? So we get the speed of sound as 180 meters per second. Okay, so we have got what? The velocity of sound in air as 180 meters per second, which is the answer for the first question. We have seen what is the velocity of sound in air. They have asked in the first question. So we got the first answer. What is the second answer? What is the second question? What is the distance between the two walls? Now we know from the given fact that one of the walls is at a distance of 360 meters. Right? So we need to calculate the distance between the other wall and then add up the two distances. Let us see. Time taken to hear the second echo. Let us see. He hears the first echo after 4 seconds and another after 2 seconds. After 2 seconds means time taken to hear the second echo will be 4 seconds for the first echo and 2 seconds more for the second echo. That means time taken for the second echo will be 4 seconds plus 2 seconds, that is 6 seconds. Now distance traveled in these 6 seconds, we can take it as 2x. Why 2x? Because again, same way, it has to travel from Sunil up to the wall and then back to Sunil. So it has to travel double the distance. That is why we have taken 2x. Now speed of sound in air, we have just calculated previously as 180 meters per second, right? So we can say, therefore, 2x is equal to 180 meters per second multiplied by 6 seconds. Now here the formula is what? Distance is equal to speed multiplied by time. We know what? Distance, sound is a distance upon time. Therefore, distance is equal to speed of sound multiplied by time. That is what we have done here. So distance is 2x, speed of sound is 180, and time is 6 seconds. So we get it as 1080 meters. So 2x is 1080. Therefore, x is equal to 1080 divided by 2, that equals to 540 meters. Right? Now, so the distance between the two walls will be what? So you have imagined that Sunil is standing in between. One of the walls is on the left hand side, other wall is on the right hand side. So the given fact here is the wall closest to him is at a 360 meters. So you can say the wall on the left is at 360 meters and the other wall on the other side is at a distance of 540 meters. So the distance between the two walls will be 360 meters plus 540 meters, that equals 900 meters, right? So the distance between the two walls is 900 meters. That is what we have calculated, the second answer, right? The next one. Now these are the extra numerical problems. These are not there in the textbook. So as we are solving them, you can take screenshots of these questions. Now, a person fires a gun standing at a distance of 55 meters from a wall. If the speed of sound in air is 330 meters per second, find the time for the echo to be heard. Right? Now, first things first. We have studied the concept of echo, and we know that the minimum distance between the person, that is the source of sound, and the reflecting surface should be 17.2 meters for us to hear an echo. In this case, the distance is 55 meters. So definitely we are going to get an echo, right? So let us see. So given is distance S is 55 meters. Speed of sound in air, that is V, equals to 330 meters per second. And time required is what we have to calculate. So time required for us to hear the echo. So we know what? Speed of sound equals to distance upon time. Right? Now, look at the value for distance that we have taken. The distance we have taken as 2s. Now, why 2s? Again, in the previous example, we have seen the sound has to travel from the person up to the wall and from the wall back again to the person. That is double the distance. So we have taken 2s upon the time t. Right? So therefore, t, the time t required is equal to 2s upon v. Right? So that is 2 into 55 divided by v, velocity, that is 330 meters per second. That comes down to 110 divided by 330, that equals to 0.3 seconds. Right? So the time for the echo to be heard when the gun is fired is 0.3 seconds. So if you happen to find a wall which is at a distance of say 55 meters from you, and if you stand over there and you happen to shout loudly or make a big bang sound, then you will get the echo in a time of around 0.3 seconds, right? Provided the speed of the sound is 330 meters per second, right? Let us see the next question. A sound wave has a frequency of 2 kilohertz and a wavelength of 40 centimeters. How long will it take to travel 1.6 kilometers? Now again, this question is related to velocity of sound, right? Now we will write down first the given things. Given frequency nu is 2 kilohertz, that is equal to 2 into 10 raised to 3 hertz, right? And wavelength lambda is 40 centimeters. We convert it to meters as 0.4 meters. Distance that the sound wave needs to travel is 1.6 kilometers, that equals to 1600 meters, right? So we need to calculate the time required. We know speed of sound is equal to frequency into wavelength, right? So hence v equals to nu into lambda, right? So we have put nu as 2 into 10 raised to 3 hertz multiplied by wavelength as 0.4 meters. So we get 2000 multiplied by 0.4, that equals to 800 meters per second. So in the first part, we have calculated the velocity of the sound, that is 800 meters per second. Fine. Now we will calculate the time required. Now we know distance, so speed is equal to distance upon time. Therefore, time is equal to distance upon speed. So the distance for the sound wave to travel is 1.6 kilometers, which is 1600 meters divided by the speed of the sound, which we have calculated above as 800 meters per second. So 1600 divided by 800, it gives you 2 seconds, right? So that sound will take 2 seconds to travel. There is a difference. Remember, the velocity of sound is different. That is why it is taken such a small time. Okay. Okay. So that is what is the numericals that we have studied today. Now let us once again go through whatever numericals they are there, right? So I will expect students to take a screenshot of these numericals, right? And you can solve it in your notebook. Okay. So let us see first numerical we solved today. How long will it take for a sound wave of 25 centimeter wavelength and 1.5 kilohertz frequency to travel a distance of 1.5 kilometers? So we have frequency nu as 1.5 kilohertz, that is 1.5 to 10 raised to 3 hertz. Wavelength lambda is 25 centimeters, which is 0.25 meters. Distance is 1.5 kilometers, which we have written as 1.5 to 10 raised to 3 meters. We calculate time. So velocity of sound is frequency into wavelength, that is v equals to nu into lambda. So v is equal to 1.5 to 10 raised to 3 multiplied by 0.25, that equals to 375 meters per second, right? Then we know time is equal to distance upon velocity. So t is equal to s upon v, which equals to 1.5 to 10 raised to 3 divided by 375, that equals to 1500 divided by 375, which is 4 seconds. Thus, the sound wave takes 4 seconds to travel a distance of 1.5 kilometers. The next question was, ultrasonic sound waves are transmitted downwards into the sea with the help of a sonar. The reflected sound is received after 4 seconds. And what is the depth of the sea at that place? Given velocity of sound in seawater is 1550 meters per second. So we write it as given. Then time taken for the echo to be heard is 4 seconds. Time taken for the sound waves to reach the bottom of the sea is 4 divided by 2, that equals to 2 seconds, because echo travels double the distance, right? Then, so we know velocity is distance upon time, and distance is equal to velocity into time, right? That is 1550 multiplied by 2. It should be 2 here. That equals to 3100 meters. So depth of the sea at that place is 3100 meters. Okay. The next question was, the speed of sound in air at 0 degrees Celsius is 332 meters per second. If it increases at the rate of 0.6 meters per second per degree, what will be the temperature of when the velocity has increased to 344 meters per second? So we have calculated this way. The speed of sound in air is at 0 degrees Celsius is 332 meters per second. That means if it increases at the rate of 0.6 meter per second per degree, then we can write an equation. Speed at x degrees Celsius will be equal to 332 plus 0.6 times x, right? Thus 344 equals to 332 plus 0.6x. So we can write 344 minus 332, that equal to 0.6x. So we can say 12 is 0.6x, or x is equal to 12 divided by 0.6, which comes down to 20 degrees Celsius. So thus the temperature of the air will be 20 degrees Celsius when velocity of sound is 344 meters per second. The next numerical was, Neeta heard the sound of a lightning 4 seconds after seeing it. What was the distance of the lightning from her? So the velocity of sound in the air is given as 340 meters per second. So the solution is, let the distance between Neeta and the source of lightning be x. Speed of sound in air is 340 meters per second. Time taken by the sound to reach Neeta is 4 seconds. So distance is equal to velocity of sound multiplied by time. That is equal to 340 multiplied by 4, which is equal to 1360 meters. So the distance of lightning from Neeta was 1360 meters. Next is, Sunil is standing between two walls. The walls closest to him is at a distance of 360 meters. If he shouts, he hears the first echo after 4 seconds and another after 2 seconds. We have to calculate what is the velocity of sound in air and what is the distance between the two walls. So the first part of the solution is, time required for the first echo is 4 seconds. That means the distance traveled by the sound in these 4 seconds will be twice, that is 360 multiplied by 2. So speed of sound is equal to distance upon time, that equals 360 multiplied by 2 divided by 4, which you get as 180 meters per second. So the first answer is, the velocity of sound in air is 180 meters per second. The second question is, what is the distance between the two walls, right? Let us see. Time taken to hear the second echo is 2 seconds more, that is 4 plus 2 seconds, that is 6 seconds. Distance traveled in this 6 seconds will be again twice the distance, right? Because echo takes double the distance. So speed of sound we have previously calculated as 180 meters per second. Therefore, distance is equal to speed multiplied by time. So we have taken distance 2x is equal to speed, that is 180 meter per second, multiplied by time, that is 6 seconds. So we get 2x equals to 1080 meters. Therefore, x comes down to 540 meters. So the distance between the two walls will be 360 meters plus 540 meters, that is 900 meters. So distance between the two walls is 900 meters. Okay. Then next was extra questions. A person fires a gun standing at a distance of 55 meters from a wall. If the speed of sound in air is 330 meters per second, find the time for an echo to be heard. So the given distance is 55 meters. Speed of sound in air is 330 meters per second. We need to calculate the time, right? So we know speed of sound is distance upon time. That equals to 2s upon t. Because it is an echo, it has to travel double the distance. That is why we have taken 2s upon t. Okay. So therefore, t equals to 2s upon v. That is 2 into 55 divided by 330. That is 110 divided by 330. That equals to 0.3 seconds. So time for the echo to be heard is 0.3 seconds. Next question. A sound wave has a frequency of 2 kilohertz and a wavelength of 40 centimeters. How long will it take to travel 1.6 kilometer? Right? So the given variables are frequency nu equals to 2 kilohertz, that is 2 into 10 raised to 3 hertz, that is 2000 hertz. Okay. Wavelength lambda is 40 centimeters, that is equal to 0.4 meters. Distance given is 1.6 kilometer, which is 1600 meters. We know speed of sound is frequency into wavelength, right? So we can write v equals to nu into lambda, that is 2 into 10 raised to 3 multiplied by 0.4, which is 800 meters per second. So here we have calculated what? The velocity first. And from velocity, we'll calculate time. We know time is distance upon speed, that is 1600 divided by 800, which is equal to 2 seconds, right? So students, we have completed the chapter over here. I hope you have taken the screenshots of the questions here, right? So we have concluded the class here, right? So any questions if you have, please raise your hands and ask the questions. Come on, students. If you have any questions, please raise your hands. Hello, madam.
Yes, sir.
Yes, madam. So we have completed the class and completed the chapter, right?
Okay,
So
sir. Okay. Thank you so
yes,
much,
we can
sir. Thank you.
end the class. Yes, madam. Thank you so much.